Welcome back. I'm glad you're joining us on this GPS journey. Today we're going to begin to break apart the GPS, and we'll talk about the 5 components in this first chunk here. Those are the main pieces of the GPS concept. Satellites, they're the ones that send the radio signals. And included in those radio signals are 2 pieces. The navigation message carries the key information, the auxiliary information that you need. Where is the satellite? When did it broadcast the radio signal that is so key to GPS? Paired with that are the navigation signals themselves. These are very carefully crafted. This is not normal radio communications. They're very, very carefully crafted to enable the user receiver, all those handsets and phones worldwide, to make a very precise measurement of the arrival time of the signal. That measurement is called a pseudo-range. And pseudo-ranging is really the fundamental thing that lies at the bottom of GPS. And we call it the pseudo-range because it's not equal to the true range by itself. In fact, it's equal to the true range plus the bias due to the difference in time measured by the user equipment from the time clock that underlies GPS. So there's a clock bias included there too. We'll come back to that soon enough. And finally, 1.10, we'll talk about performance. And today the performance of GPS, just to give you a heads up, is about 5 meters. Now that's for a standalone receiver. That's something that you just hold in your hand and you operate it by yourself. If you want better performance, in fact, much better performance can be achieved with differential GPS. And that means you have 2 stations and you navigate the rover relative to the reference receiver. And in those kind of configurations, you can get 1 meter accuracy, you can even get 1/10 of a meter, and you can even get 1 centimeter if you like. So here are those same concepts we just went over, depicted differently. In this view graph, we show the GPS as a red clock on the far right there. Let me just sketch it for you. And it's orbiting, following this black dotted trace. And by the way, it's moving quickly. It's going at about 2 miles per second, so it is moving very quickly. Having said that, it's so far away that it will spend hours in the sky of an individual user from the time that it rises in the sky to the time that it sets in the sky. So, in addition to the satellite, there are those 2 pieces of information that we already talked about. Item number 1 is knowing the time of signal transmission. So that's that precise clock on board. And you should know that one of the enabling technologies for GPS was how to build and how to deploy and how to engineer space-qualified clocks. And so that's something to keep your eye on. The other thing that's important, not only do we have to know the time at which the satellite transmitted, we have to know the location in that black dotted orbit from which it transmitted. So item number 2 is the known satellite location. This is another big enabler of GPS. How do we get to know where the satellites are to about a 1 meter accuracy in real time? So it was already known at the time before GPS how to get 1 meter so-called orbit determination, but to do it in real time was a very, very difficult thing. The third item is knowing the speed of the wave as it travels from the satellite to the user. And that speed is pretty close to the speed of light. There are a couple of things that slow the wave down, and those are fairly well modeled. So all told, we can say that we know the speed of the radio wave pretty well. And the fourth item is measuring the arrival time accurately. And that's the job of every single receiver that's held or carried by people, cars, ships, and airplanes. And that can be done to about 1/1000th of a second. So when all that goes well, the accuracy you get is shown on the left side of the plot. And that scatter, that red omelet sitting there, is really just a report on many location estimates made by the receiver. And if you look closely along the horizontal axis, that's plus or minus 5 meters. And as you look, if you look at the vertical axis, that's also plus or minus 5 meters. And so this circle drawn here is a circle with radius equal to 5, and the entire scatter resides inside of there. And that's the nominal, typical performance of GPS in the so-called standalone mode. So let's take on the first component, satellites. Satellites are the ones that send the radio signals. They send those navigation messages that carry the key information that we talked about. And they also broadcast the navigation signals. So they're where the story begins, really. And here we have a picture of the GPS constellation of satellites today. In a little while, we'll come to all the satellites being launched by the Europeans and the Russians and the Chinese, Indians, and Japanese. So the GPS satellites are the ones that occupy these orbits shown in here. And for reasons that I hope are clear to you, that's called the GPS birdcage, because it's looking a little bit like a birdcage. And the other thing that's true about these GPS satellites, they're in so-called medium Earth orbit. So at this altitude, these are MEO. If we go further in, way close to the Earth, that would be LEO, low Earth orbit. And these satellites way out here are called GEO. And GEO has a slightly different meaning to the acronym. It's geostationary or geosynchronous satellites. So the LEO satellites are not used for satellite navigation. LEO tends to be mostly occupied by surveillance satellites, Earth observation satellites, spy satellites, and of course they want to be close by so they can actually take photographs of the Earth's surface. In principle, we could have put navigation into LEO, but it would have required way too many satellites because the footprint of an individual LEO satellite is very small on the surface of the Earth. So the amount of coverage you get per satellite is small. So we back up to MEO, and the great benefit of doing that is as we move out to MEO, the footprint, the visibility for each satellite gets to be a large fraction of the Earth's surface. So typically a GPS satellite out there in MEO can see about 1/3 of the Earth's surface. So we don't need so many satellites in MEO to cover the whole surface of the Earth. Notice that we also include GEO in this picture of GPS, and that's because there are certain satellites in geostationary orbit that are used to augment GPS. And that's done regionally. So for example, the US has 3 satellites in GEO that add information to GPS. The Europeans have 3 satellites there. The Japanese have 1 satellite there. The Chinese have satellites there. And GEO is used when you want to have a satellite that is fixed relative to the Earth's surface. So as the Earth rotates, the geo-orbital velocity is exactly matched to the rotational speed of the Earth. And so that has this great advantage that you're expending the money to put a satellite in orbit, but it really does serve your part of the Earth. So this is a good capture, a good look at what GPS looks like today. If we hop to this next view graph, what we've done here is included GPS. You can still see that birdcage blurred in there in the middle somewhere. But we've added the other satellites that are available today from Russia, from China, Europe, India, and Japan. The Russian system is called GLONASS. It has about 24 satellites in view. The European satellite system is called Galileo, only 4 satellites so far. The Chinese is called Beidou, which is Chinese for Big Dipper, drawing its name from the famous constellation of stars. And there are about 16 Beidou satellites on orbit today. Japan has a system that's really very, very well tailored for navigation in cities, and it's called the Quasi-Zenith satellite system. We'll come back to the idea there at the end of the course when we're talking about future of satellite navigation. India has IRNSS, which stands for India Region navigation satellite system. That's the situation today, how GPS and its sisters look worldwide. In another 10 years, there will be almost twice as many satellites as you see there. So that's amazing. We'll really go to a very, very heavily populated medium Earth orbit and geostationary orbit and inclined geosynchronous satellites. And that will be probably about 120 satellites or so that we'll have. Here's a timeline. And it tells the story of the growth of GPS. On the far left would be 1973. That's when GPS was approved by the Department of Defense for a deployment, or at least a prototype deployment. And remarkably, it took the designers only 5 years to get 4 satellites on orbit. That's an incredible feat in of itself. Today, it would take quite a bit longer than 5 years to go from initial approval to that time that the satellites were already there. And in the 1970s, we have slow development of the prototype of GPS, just a few satellites, and so the test of the user equipment happened on the ground using equipment similar to what this soldier carries, shown there in the lower left. And what he has in his hand is just the display for the information of GPS. And what he carries on his back is the real guts of the receiver. Notice that it was very, very big compared to anything that we would imagine in our cell phone today. And the big stick up over his head there is the antenna. In fact, he was testing this receiver based on satellite signals broadcast from pseudo-satellites on the ground and going in and being captured there by that antenna. As we move into the 1980s, the constellation gets richer and richer, eventually getting up to 16 satellites at the end of that decade. Shown below is a first civil user of GPS, and that's a surveyor. He's doing land survey, and he's carrying the GPS antenna on a stick so he can have it nice and high up above any effect from his own body or any nearby object. He too has the receiver on his back and a display head in his hand, so it's not unfamiliar relative to the soldier. But this was really an extremely important part of the GPS evolution, because there never would have been enough military receivers to really enable economy of scale in the manufacture of receivers. But when the civilians began to have their applications, not so much with survey, but as we move into the 1990s, the consumer and commercial applications of GPS took off. There you see the first of the so-called handsets for GPS. At the same time, the constellation is getting richer and richer, and so 24-hour performance is available, and we're beginning to get towards those 5-meter accuracies that we talked about. As we go into the current decade, let's say this chunk right out here, the constellation has continued to be rich, and in fact, here in 2014, there are 32 satellites on orbit. So it's remained constant at around 31, 30, 32 satellites, something like that. And that's been true through the last decade. The amazing thing that's happened in parallel is that the consumer use of GPS has enabled these extremely small GPS receivers that go into the cell phones. And the full bill of material for that tiny little receiver is about $1. So the cost of a GPS receiver has gone down dramatically.